One for dandelions in the air at both of us. So.
All right.
No, it was David.
Here we go. So, a series is when you add up terms of a, not you, Siri. A series is when you add up the terms of a sequence. This is gonna get old here. So for example, let's say we have the sequence. Oops. A sub n equals 2n minus 1. If I enumerate that sequence, that's just our positive odd numbers. And then our series then, we'll use S sub n to abbreviate that. Is just the terms of the sequence added together. Is everybody okay with that? So if I was to talk about S3, that's just the sum of the first three terms of our sequence. If I talk about S7, that's the sum of the first 7 terms of our sequence. 5, 6, 7, which is 14 times 2, or 14 to, okay, 49. Does everybody feel okay with the notation here? These guys are called like partial sums because they're just, we've added up part of the entire sequence. Because how long does that sequence go? Forever, right? We're just adding up part of it, so this is a partial sum. We added up the first 3 terms, or the first 7 terms, or the first n terms. Everybody feel okay? Okay. So, first things first, is it real convenient? What if I asked you to write down like S27? That's a pain in the tuchus, right? So we're going to create a new notation called a summation or sigma notation.
Sigma.
Yep. That's the Greek letter. So, for example, we can say that S3 is going to be the same as we write the capital Greek letter sigma, which looks like this. And then we're going to write the sequence that we're going to be adding up. So that was 2, and I'm going to use the letter K here just so that I don't abuse this letter N. K minus 1. So that's telling us what the sequence is that we're going to be adding up. And then below, we're going to write the term that we start our addition with. So we're going to write K equals, and because we started by adding the first term, we'll say 1. And we end with the third term, so on top we're going to write 3. Is everybody okay with the notation here? We're going to do 2 examples to practice. We're going to give you a sigma notation, ask you to expand it into a series. And then we're going to give you a series and ask you to compress it down into a sigma notation. Emma, what's up?
I'm just confused about the sequence.
That's the explicit formula. Remember?
All the way back up.
Yep. So it's the same thing. I just traded the n for a k, so we didn't abuse that n, which was doing a lot of work already there. Since it was representing a term number above, I didn't want to use n again and have it be confusing. And it's like, is it the same n? No, it'd be a different n. Just use a different letter. All right. So let's go from sigma notation to a series. Oops. Okay. So here is our sigma notation. So when I read this, I'm going to read it as the sum from the first term to the 5th term of this sequence. Is everybody okay with how I'm reading the symbols? Okay. Watch.
I am. I am
Okay.
not taking notes.
I know, but like it's hard to take notes and watch at the same time sometimes when I'm like
Okay.
highlighting. You know what I mean?
I just need a second for all of the numbers and to like lock in their meanings.
Okay.
What is that? Like, what do you call that?
That's the capital Greek letter sigma.
Oh, suffixation sigma.
So this is a sigma notation we're looking at.
No, that is what I thought. That's just no.
Okay.
Wait, one last question. This
Yes.
is gonna sound so stupid. Why are the I equal, that was stupid, I'm trying to figure it out.
Okay. All right. So this is telling us we're adding up the first through the 5th terms of the sequence 32 times 1/2 to the I minus 1. So for me to write the series, I need to plug 1, 2, 3, 4, and 5 into that formula and like put the plus signs in and like yada, yada, yada. So there's the first term. There's the second term. There's the third term. Forgot how many we're doing. Here's the 4th term. And then there's the 5th. Ooh, boy. There's the 5th term. So now if I just simplify things down, if I add those two up, all that stuff up, I think I get 62.
We asked to write out that formula with all the things filled in, or do we get to just use the inconvenient way?
I will ask you to be able to go back and forth from sigma notation to the expanded form and the expanded form back to the sigma notation. Okay. Which is a fair question. Okay, so here we're going to go from the series to the sigma notation. So the first thing that I'm going to want to do is I'm going to want to look at those numbers that we're adding up and see if they come from, or see what type of sequence they come from. Because eventually I'm going to have to be able to write the explicit formula for that sequence. So if I look at this, it looks very much like an arithmetic sequence, because I don't know a number that's going to multiply by 7 to get 19, and then 19, or by 19 to get 31. But if I look, it looks like we're adding 12 each time, right? So I know this is an arithmetic sequence. I know D is equal to 12, and I know the first term is 7, right? So I can write my explicit formula. So that's going to simplify down to 12n minus 5. So if I start writing my sigma notation, actually, let's see. So I know I have that much. Everybody's okay? What's the problem, Emma?
How did you get 12n minus 5?
I distributed the 12 through and then combined negative 12 and plus 7. Is that okay? So the only things left that I need to do is I need to fill in the lower bound and the upper bound, right? So if I look at the the series up here, looks like I'm adding 1, 2, 3, 4, 5, 6 things together. Everybody agree with that? So I'm going to have the first term through the sixth term. And there's my sigma notation. Is everybody okay there, Gabby?
Is it always
Oh, I meant that was supposed to be a 12K.
Oh.
Sorry.
Is it always K equals 1?
It can be. So you have a little bit of freedom there. Because if I had decided, for example, Emma, like something silly like, oh, let's say this I mean to be the fifth term. So we're adding up terms like 5 through 10.
Are you going to throw any of those in the test?
I'm just saying you could. You said, is it always? Right? And I'm saying, no. You could do something like this, where you're going to write the formula, and this is if this is the fifth term, you can write it like this, and you can simplify it down. You get a different value for this, or different equation for your, or explicit formula for your sequence, which is fine. And then that's going to be 53. So you could write it that way. It'll give you the same result. I don't know why you'd want to do that, but you could, because you said, is it ever? So it's like, that's a different question than like, would I?
Okay.
Yes, Daniel? Sure. So everybody, we doing okay so far? Mr. Kulik, can this get harder? Well, I can put one little twist on it. The little twist I can do is I can make it harder to find that upper bound. Well, how would you do that? I don't even understand what that would look like. Well, what if I took this same sequence or the same series, but I did something like this? And I did that. Emma?
Isn't that just like the common difference if you're doing it? Or ratio, common ratio?
Sure, it could be. I mean, you could do it that way. But we have no indication as to how many spots are in between. So what probably is going to be the easier route to go is we'd start the same way. You know, like we'll notice that, like, okay, you know, it's still arithmetic. The D is still 7. The D is still 12, and the first term is still 7. Oopsie daisy. So, you know, we still do this stuff. And we still have this. So this is the first term, this is the second term, but what term is this guy? We want to know the n for that. So if I just plug that into my explicit formula as the a sub n, I can solve for n. So there I've hidden how many terms there are, so you can't just count them. You have to take that last term value and plug it back into your explicit formulas to solve for n. Okay, so that's one set of skills, going from sequence to sigma notation or sigma notation back to sequence. I'm sorry, series. Series to sigma notation. And then sigma notation back to series. What we want to do next is we want to look specifically at how to compute those partial sums, like what the actual addition is, without having to enumerate the entire sequence and add them all together, for specifically arithmetic and geometric. So we say that an arithmetic series just adds up the terms of an arithmetic sequence And then we would say the same thing about a geometric series, is just adding up the terms from a geometric sequence. So I'm going to not write the same formula or the same definition there twice with two different words chained. Is that okay with everybody? So for an arithmetic series, our formula to calculate that sum is the first term plus the last term times n over 2, where n is the number of terms we're adding together, right? Just double check that real quick. Okay, good. So far, so good. Okay. So here we're trying to add up all these things together. What's the problem with adding them all together? We don't know all of the things we have to add together, right? So first things first, we want to look to see if this sequence is arithmetic or geometric. What do you guys see? Yep, and what's the pattern? It's minus 15, right? Gosh. So it looks like these are terms from an arithmetic sequence where the d is negative 15 and the first term is 8. So again, we can write our explicit formula. Everybody's okay there? Now, what do I really need this explicit formula for, Mr. Kulik? Like, I have the first term and I have the last term, right? So in my formula, I have this and I have this. I'm going to need the explicit formula, though, to get that in. So to do that, I'm going to take that negative 608 and plug it in for a sub n and solve for n. So we have n equals 41. So we would say then the sum of the first 41 terms of this sequence is the first term plus the last term times 41 over 2. I'm going to enter that into my calculator. I get negative 308. Oh, no, I don't. I missed the 4 on the 41. I was like, that can't possibly be right. Negative 12,628. What do you guys think on that? Okay, it's just because you're not familiar with the notation yet. It's really equally difficult because you need all the same information. You're just using it in a different formula and putting it into the sigma notation. But you're really doing the exact same algebraic steps. Okay? Like once you've gotten to here, you need all that same information doing either problem. It's just what you do with that information afterward. So the beginning is the identical. Okay? Let's do another one. Okay. What's my first step? Very good. So I want to see if these numbers are the terms of either an arithmetic or geometric sequence. In the situation that I'm giving you, they will always be that. Unless it's a calculator-only problem that we haven't talked about yet. Okay. What does this look like to you guys? Yeah, what's the key or the key observation that tells you this better gosh darn be geometric? Yeah, the alternating signs. Very good. So to go from 64 to 96, what did we do? I can just divide negative 96 by 64 and then reduce, right? That should give me the common ratio if you don't see it by hand. That's negative 3 over 2. If I take 144 and divide it by negative 96, also gives me negative 3 over 2. Everybody feel good so far? I'm now going to write my explicit formula. Since it's geometric, it's a different formula though, right? But no big whoop. Everybody doing okay still? Okie doke. So now we need to figure out the n. That's the last piece in our formula, right? If I go back and I look, we have the first term, we have the r. What we don't know yet is the n. How do I find that n? Well, I'm going to plug the last term of my sequence. In and solve for n. What do I need to do first algebraically to get that n by itself? Divide both sides by 64. I'm going to think about it as multiplying by 1 over 64. Same difference, right? The only reason is I have a fraction on that left-hand side, so it makes it a little bit more convenient. Is that okay with you guys? Now, what do I need to do to get the n by itself here? Where is that n located? In the exponent. What do I need to do to both sides to get a number out from the exponent? No. What? Not quite. We just did this, guys. This is chapter 15. Back to haunt you. We have to use a logarithm, yes. Which logarithm would we want to use? Log base. Okay, negative 3 over 2. Good. One small problem, though. Does anybody see the problem with what we're about to do? Log bases can't be negative, and we can't take the log of a negative number. Here's the deal, though. This problem is equivalent. We'll have the same value for n as this problem where we drop the negatives, right? You guys agree? If I take, like negative 2 to the n is equal to negative 8, has the same answer as 2 to the n equals positive 8, right? So I can do the same thing here. That gets rid of our negative problem. And we're good. So we'll do log base 3 over 2 to both sides. And we know that those guys cancel each other out. And if I go into my calculator, I do log base 3 over 2 of 2187 over 128. I get 7. And then I add the 1 over. That's what I needed. Yay! Yeah, you press the math button and pick Command A at the very, very bottom. So keep scrolling down until you see the log base command. What? Yep. And you just type it in just like it looks like on your sheet of paper.
Not how did you type it in, but why? Like which part number? What numbers did you type? Just log base 3 over 2.
So this is what I typed into my calculator. All right, so that's everything we needed, right? Now we can fill into our formula. So that's going to be the first term times 1 minus negative 3 over 2 to the 8th over 1 minus negative 3 over 2. And the answer that tumbles out of my calculator when I do that is that boy right there. So, okay. So basically all I'm doing is using the stuff that I know about sequences to get the information to pool into these formulas, right? It's basically just pooling stuff into formulas again. So it's not so bad. Two more little things that'll both be relatively quick. So what we've just been doing are finite sequences, because there's like, you know, the first 5 terms or 22 terms or 175 terms or whatever, right? But there's a fixed amount. Yes? What about infinite sequences, where we're adding up infinitely many things? So I gotta say I have one little qualifier. I said all, but all of them except the sequence that's just every term 0. If you add up infinitely many zeros, you still get 0, right? But we say all non-trivial arithmetic sequences are divergent, or series, I should say. That's the wrong word there, Mr. Kulik. Series. And divergent means that one of 3 things is happening. Either it adds up to give you positive infinity, it adds up to give you negative infinity, or just something that can't be determined. So an example of a sequence or a series that when we add it up, we can't determine what the answer is, would be like if I'm adding up 1 plus negative 1 plus 1 plus negative 1 plus 1 plus negative 1, and I'm doing that forever. Not undefined, indeterminate, which is different than undefined. Undefined really means infinite. Indeterminate, well, that series that I just described could have one of 3 answers, right? The answer could be 1, could be 0, or could be negative 1. But there's no way to tell, because it's based on like whether you had a multiple of, you know, like the number of terms had a remainder 1, 2, or 0 when you divide it by 3. And there's no way to tell that because infinity you can't divide it by 3. So it's impossible to tell. That's what we mean by indeterminate. Okay, so a divergent series could result in any one of those 3 outcomes. I don't care if you're able to tell the difference. You just need to know that, like, hey, that's a problem I can't do. Deal? Okay. Bad news is that only some geometric series are divergent. So if the absolute value of the common ratio is less than 1, the infinite geometric series has an answer. It converges. Now that's pretty strange, right? You add up infinitely many things and you get a finite answer. But indeed it is true. And the formula for calculating that is just the first term divided by 1 minus r. Really easy formula, right? If that r value is greater than or equal to 1, then it's divergent. We don't have to deal with it. We just say that it's divergent, move on about our day. What do you guys say to that? It's okay? Do we need to do an example of that, or is that fairly straightforward? Yeah, I think that's pretty straightforward. All right, last thing I want to do is just some calculator piece. So let's say I wanted you to compute the sum described here using sigma with sigma notation. This is a pure calculator problem. Let me fire up my guy here. Somehow I got that window closed. Oh, good, error. Oh, good. Several seconds to refresh. Yup.
Why is this one parentheses?
They mean the same thing. So no good reason. Because I forgot that I done brackets for the other one. How's that? I know that's not very reassuring or whatever, but that's the honest answer. And honesty is a pretty good policy. All right, so here we go. So to do this on our calculator, we just want to be on the main screen here. And I want to press this math button. And I'm going to scroll down until I see the summation command. And now I can type this into my calculator exactly like it looks like on my sheet of paper, other than instead of using the letter I, the variable on my calculator is going to be X. Okay? And what was it? Minus 15, 17. And then you just press enter, and boom, there's your answer.
That's it.
Yeah.
Okay, that's it. 5.
Oh, yeah, no, that's supposed to be a 51. That's my bad penmanship, so we'll chalk it up to that, Daniel.
Yeah.
What do you guys think? Okay. So I think that's it for today. You guys have a Delta Math.
No.
Delta math.
I didn't know that.
Yes, go ahead. So this is the last Delta Math for the year. I know, it's exciting. So asks you to evaluate the summation. How are we going to do this? Use the calculator. Just use the calculator. Type it in, press enter, move on. Here is what type of sequence is this one adding up? If I look at this explicit formula, what is this? arithmetic. Try to use the formula for the arithmetic sequence that I gave you guys. So you'd plug 5 into this, that'll be the first term, and 66 for that, that'll be the last term. Okay? And then you'd have to figure out how many terms are there between 5 and 66. That'll be your n, and that should do it. Oh, if I go back, how would I want to check that I did it correctly? Type it into the calculator, right? That'll be a great checker. Same idea here with geometric series. Okay. Here it's going to ask you to take a series and convert it to sigma notation, just like we practiced. Here we're calculating a geometric series. So it's giving you the first couple of terms and then asking you to find the sum of the first 8 terms. So again, write the explicit formula, plug 8 into it to find, well, you don't even need that, right? Because you have the first term and you have the n. So you just plug it into the formula. There's nothing more to it than that. Here, or the next level of this is where they don't give you the n. You have to solve for it, like we did in the example. Here's, they don't tell you whether it's arithmetic or geometric. And then this is an infinite geometric series, and you just decide if it is, so if it is geometric, you have to give the r, and we say this series diverges because the r is greater than negative, or less than -1, or greater than +1. So you just would answer it like that. Oh, what did it happen here? It's definitely 2, diverges. Oh, sorry. Yeah. Includes, the diverging is including 1 and -1. Excuse me. And that's all she wrote. Those are the different types of problems in the Delta Math. This Delta Math due the following Sunday. Okay, and we'll have another day with worksheets like we did last class next week to practice series stuff. And then it's test review and test time. I think all the assignments for the semester are now up in My Notre Dame, so you can look at everything that's left to do. Reminder, for this Sunday, you have 2 Delta Maths. A lot of you guys aren't very far. I looked at it the other day. I'm really proud of you, Gabby. Thank you. And then you have your worksheets that we did in class. Again, every 4th problem, depending on what group you were in, and you had assigned a problem to start at, whether it was 1, 2, 3, or 4. And that's it for Sunday. Well, after this week, for next week, we'll have 1 more Delta Math and 1 more set of worksheets, and that's it for assignments. And you have 1 more test, and we're in and we're out, and it's good to go. How do you guys feel?
Good.
How's this chapter treating you? This shouldn't be so bad, right? It's mostly just like, do I understand the formulas and how to use them? And if you do that, everything goes pretty well. You just got to get past the notation. But it's pretty simple, the ideas here. We're just kind of like using the formulas to find values to plug into other formulas, and that's kind of the gist of it. Emma, how do you feel after today? Tired. How did your understanding go? Was it okay?
I had to fight for it.
You had to fight for it. I know, it's the end of the